Okay, once again, let me welcome all of you back to another session of organic chemistry. In today's session, we are going to start our discussion on chapter 24. Chapter 24 is concerned with the chemistry of amines. Okay, but before we start the discussion on chapter 24, let me make a few announcements. I want to remind you that the next class exam, which is exam number 4, is scheduled for next week, Thursday. That is April 24, and that is the last day of class. And also for the graduating seniors, your exam is scheduled for next Wednesday, which is April 23rd at 6 p.m. That will be in room G8 of the chemistry building. By the way, how many of you are graduating seniors? Okay, not too many of you. Okay, very good. So
I think it's more.
Okay, that will be on Wednesday, April 23rd at 6 p.m. in room G8. Also, the homework assignment for this week, that is due on Sunday, April 20 at 11 p.m. And finally, because of the exam number 4, we are going to have an online review session on Monday. That is April 21 at 8 p.m. So I will send you a reminder for that session. Yes. Say that again. Yeah, the seniors have to take both the final exam and exam 4. Thank you for asking that question.
Oh, we do that on Wednesday?
You take the you take the final exam on Wednesday,
right,
and then you take exam number 4 on Thursday with the rest of the class. And then once I finish grading your exam, I will send your grade to the registrar's office before I leave my office on Thursday. Okay. Okay. So now let us. I know you guys want to go over the quiz question that you have just taken. So let us do that before we start with our discussion on chapter 24. Okay, Erin, can you read this for us?
I'll read.
Okay, go ahead.
It's okay, I understand. Provided synthetic steam for the following Robertson annulation products using starting materials with 5 carbons or less.
Okay, thank you. So what this question is asking you to do here is to provide the synthetic scheme for Robinson annulation reaction using starting material that contains 5 carbon atoms or less. Of course, as we know, in order for you to do this question, you got to know that Robinson annulation is a combination of what? Michael addition plus what? Aldo condensation. Very good. So once you know that, and then you take a look at this molecule here, they want you to make this starting from molecules that contain 5 carbons or less. The first thing you have to do, if Robinson annulation is a combination of Michael addition followed by aldo condensation, Then what we want to do is we want to go backward, starting with the aldo condensation, taking a look at this molecule here. So if we take a look at this molecule here, let me go ahead and number this. Okay, let us call this carbon number 1 right here. We call this 2, 3, 4, 5, 6, 7, 8, 9, and 10. Okay? Now, if you take a look at this molecule here, and we want to make this molecule directly from an aldo condensation, which of these carbon here will be your nucleophilic carbon and which will be your electrophilic carbon? Knowing fully well that in aldo condensation you need an enolate, and then you need the carbonyl of either a keto or an aldehyde. Yes. Nucleophile will be carbon number 2, this here, right? Okay. Okay. Very good. Why do you say that? Next to the carbonyl. Okay. Alpha to the carbonyl. Very good. So in other words, what you want us to do here? You want us to clip this molecule right here, because we want to generate the enolate on this carbon here. So, and therefore this will be your electrophilic carbon, the carbonyl, and this here will be your enolate carbon. So let us go backward. Say we have this. Is this correct? Is that correct? Is that what you're trying to do? Okay. Everybody agree? In other words, what we are going to do here, if we take this molecule here, take hydroxide, to use ethanol as solvent, we generate the enolate here, and then the enolate will attack this carbonyl, and eventually you are going to form an aldo, and then there will be dehydration. You lose water to form an alpha beta unsaturated system right here. Okay? Okay, now, oh sorry, there is something missing here. This metal here. Okay? Okay, so that is the molecule that will give us the aldo condensation. But for this synthetic scheme, they told you have to start from, of course, molecules that contain 5 carbon or less. So at this point, we want to do, so now we've done the aldo part. Now we want to do the Michael addition part. So let me go ahead and see number this. This is still our carbon number 2 right here, right? And this is our carbon number 1, and this carbon number 3, 4, 5, 6, 7, 8, 9, and 10. Okay. Okay. Taking a look at what we have here. Okay. Now keep in mind for the Michael addition, you need an alpha beta unsaturated system, and then you also need a nucleophile. Okay. In this case, the nucleophile will be an enolate anion. So if we take a look at this, which of this carbon will be your nucleophilic carbon, and which will be your Michael system? Yes. 7 will be your nucleophilic carbon. Very good, excellent. And then the carbon-carbon double bond. Between 8 and 9? Very good. So in other words, what you want us to do here, we are going to clip this right here. Right? So we go backward again. We say we are going to have this. Okay, so that would be the Michael addition system right here, the alpha beta unsaturated system. And how many carbon does it have? 1, 2, 3, 4, 5. So that means the requirement of what you have to do, 5 carbon or less. And then on this side here will simply be a nucleophile, okay? I mean your carbonyl carbon. Okay, so this will be your, you generate your nucleophile right here, enolate ion here, and this will attack this carbon here, the beta carbon, the pi electron goes here, and then when you add the dilute acid, you will protonate this, and thereby by getting this here. Okay, so the reagent you need for this is you could use hydroxide again, using ethanol as solvent as step 1, and then step 2 to add the dilute acid. Okay, is that clear to everybody? Okay, so this kind of question here, implicitly what they are actually asking you is you must know the reaction mechanism, or you must know what Robinson annulation is, and meaning that you also need to know exactly what, in this case, Michael addition reaction is, the mechanism, and also the mechanism for the aldol condensation, even though they are not asking you for the mechanism. Okay, so anyway, so for this, you need to start with this, react with this in the presence of hydroxide. This here generates this will generate your enolate. And once you form your enolate here, do your Michael addition, attach this here, pi electron goes here, and then you subsequently will protonate this here to obtain this product right here. And then once you get that, then do your aldol condensation. So this is our aldol. And here is our Michael. Okay, so let's do the next one. Okay, Marshall, can you read this first?
Provide a mechanism for the following transformation. Hint, it is a retro-Claisen condensation reaction.
Okay, thank you. Okay, so here, this is another reaction mechanism problem. Here we have given you a hint. This is a retro-Claisen condensation. In other words, it is a reverse Claisen condensation. Okay. Okay, now, so you have this product here from the Claisen reaction. That is what essentially what this is saying. And now you want to now react with ethoxide, ethanol is the solvent. You notice how easily this reaction goes, this room temperature reaction right here. And then you generate the ethyl acetate. And this other ester here. Okay. Okay, so anybody wants to give this a try? What is the first thing that will happen here for the mechanism? What is the first thing that happens? The ethoxide attacks the carbonyl because this is going to be a reverse Claisen condensation. Very good. So you have the ethoxide, come in here. I put all of these electrons here. Okay, attacking carbonyl, and this pi electron comes to oxygen, and so we have this. And we have this here. Okay, now what is going to happen next? Reform the carbonyl. Very good. We are going to reform the carbonyl. And if we reform the carbonyl, since we say this is going to be a retro-Claisen, we do not expect to lose the ethoxide. This time, we are going to lose this here. The carbon-carbon bond will break. So in essence, we are going to form an Annulate. Okay? And so we now have this. So that is how we form this here. That's how we form that. And then here we have this. Okay, so you form that Annulate. And then what happens now to generate this product here? Starting material, the ethanol. Okay, okay. Keep in mind at this point that you have ethanol in the system, so therefore you have. Actually, when we did this here. Okay, so. This Annulate here will grab this proton from the solvent. Okay. So at this point, we are regenerating the ethoxide. The ethoxide that we use here, so in essence, the ethoxide is just acting as a catalyst. We are going to regenerate it, okay? So we form this here plus ethoxide, okay? Okay, so, and that is the mechanism they are asking for. Okay, so let us go to the next one. You got this down? Okay. See here. Olulade, can you read this for us?
The reaction below is a carbonation of aldol type reaction. Followed by
Okay. Thank you. Okay, so this reaction here, what they are telling you, it is an aldol type reaction. In other words, you could use the concept of the aldol reaction in this particular transformation, and then also followed by the carboxylation. Okay, so you must have some idea what aldol condensation is, or aldol reaction is, and then the carboxylation. Okay, of course, we also know that we are using here ethyl malonate, and you know what happens when you do a malonic ester synthesis. Okay, you eventually will have to do the carboxylation. So, what will be the product of this? Okay, let us see. Let me see if I could give you some help. Well, as a matter of fact, let us go ahead and give you mechanism for this. Okay, what is the first thing that will happen? Nobody's asking you for the mechanism, but let us go ahead and do the mechanism. What do you think will happen first? You form the inolate using the malonate? Okay, very good. So we have this. We have 2 hydrogen here. So this comes here. We grab this here, and this electron stays on this carbon. So now we form the inolate of ethyl malonate. And then what happens to that? Attach this carbonyl. Okay, very good. Okay, so attach that carbonyl. And this pi electron goes here. Okay, so now we form this. So from this intermediate, okay, so we form this here. Okay. Okay, so now what happened after that? What do you think happens after that? What happens after that? Okay. You expect to protonate this here, right? Okay, very good. Okay, keep in mind at this point we also formed ethanol. Because this grab this here, we form ethanol. So this will now pick up the proton from the solvent to regenerate that ethoxide. Okay, so the ethoxide here is simply just acting as a catalyst. Okay, so now we have this. Okay. Now, what happens now? We apply the acid. Okay. The acid will hydrolyze the ester to what? To carboxylic acid, right?
Yes.
And at the same time, we are going to dehydrate this here. Okay, lose this hydroxy group and an hydrogen here. So we are going to lose water. So now we have this. Okay. So what, at this point, when you apply the heat, you are going to do the carboxylation, okay? Which is your typical malonic ester synthesis type reaction. Okay, so what happens? We lose this here, carbon dioxide, and this hydrogen here. This hydrogen here will come to this carbon here, and then we'll get this product. Okay, and that is the product you are going to get. So that is the product of this particular transformation right here. Okay? Okay, and that is what they're asking you to do. In other words, this molecule here, okay, will react with the ethyl malonate to give this product right here. Okay, let's go to the next one. Okay, this is the last one. How many people did this? Okay, very good. Okay. Okay, now in this particular reaction here, let me see who. Okay, Clara, can you go ahead and read this for us?
The transformation below surface of microaddition, then followed by an alkyl reaction, no condensation. Provide a mechanism. Okay,
provide a mechanism. In other words, what they are telling you here, this is a Robinson annulation reaction. In essence, this is a Robinson of course, you know Robinson annulation is a Michael addition reaction followed by aldo condensation. But in this case, we have to say followed by aldo reaction, since we are not going to lose water, so no condensation. Okay. To help us out, let me go ahead and number this. Say this is carbon 1. Oh, let me use a black pen. Let's call this carbon 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, and 14. Okay. Now, if you take a look at this, keep in mind, they already told you the first thing that happens is a Michael addition reaction. So if we are going to do a Michael addition reaction, which carbon here will be your nucleophilic carbon? Which carbon? Which one? 3? Okay, very good. So in other words, you want to generate an enolate here. So if you say that is your nucleophilic carbon, in essence, you are therefore saying you are going to join this carbon here to carbon number 7. So that is what will give you your Michael addition. Because the pi electron goes to carbon 8, and then when you protonate, you are going to now form your Michael addition product. Now, so once you form your Michael addition product, okay, once you form your Michael addition product, now you need to now do your aldo reaction. Okay, for the aldo reaction, you know you need a nucleophile, an enolate anion. Okay, which carbon here will be your inolate carbon, and which carbon will be your electrophilic carbonyl carbon? Okay, which one? 1, okay. So 1 will be your, so this here, 1 will be your inolate carbon for the aldo reaction, and then you want to use 9 for the, okay, very good. So in other words, we are going to join this. 1 and 9, okay? You have to be able to see that. Okay, so now that we know that, let us now go ahead and give the mechanism for this process. Okay, what is the first thing we need to do? What is the first thing we need to do? Generate the inolate. Very good, inolate, very good. So therefore, so we say we want to take this. Use hydroxide to generate the inolate. So what I do, I come here, this here to grab this proton here, and that will leave the bonding electron to this carbon right here. Okay, so now let us write this. So we have this here. We have this here. We have this. And then we have this here. And of course we have on carbon number 5. This is 1. Let's go ahead and number this. Carbon 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, and on carbon 5 we have the branch, and so that is 12, 13, and 14. Okay, so now we form the inolate right here. Okay, so now what is the next thing that will happen in the reaction mechanism? Inolate attacks with carbon. Carbon 7, very good. Okay, attach carbon 7. Let's get this out of the way. And this electron comes to carbon 8. Okay, so now we form this intermediate. Okay, so we have, let's number this here. This is our carbon number 3 right here. Carbon number 7 right here. Okay, so therefore, we have this here. Okay, so number this. So these are carbon 1, carbon 2, 3, 4, this is 5, this is 6, 7, 8, 9, 10, 11, and of course right here on carbon 5, and this becomes our 12, 13, and 14. Okay, now we form the enolate on carbon this here as a result of the Michael addition. Now what is going to happen next? A protonation of the enolate? Okay, very good. Okay, by the way, keep in mind when we did this, we also generated some water here. Have it here. So now that water will protonate the enolate, comes here. Enolate grab this proton here, will regenerate the. So keep in mind the hydroxide is simply acting as a catalyst here, and then we form this product, Michael addition product. Okay, so we number again. Carbon 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, and 12, and 13, and 14. Okay, now what happens next? What happens next? We have hydroxide here somewhere. Keep in mind when we protonate this hydroxide comes here. What happens next? We form the enolate, okay? Now ready for the aldo condensation. So this comes here. Grab this. Comes here. Let me take this out of the way. This number 1 here. Okay, so now we are going to form our enolate. Okay, so now the enolate will now do what? What will the enolate do now? Attack the carbonyl now. Very good. Okay, now from this. Okay, so we now form this. Now, what is the next thing that will happen to get to the product? Let me get all of this out of the way. This is where we want to go. What will happen now? Now, keep in mind we have, when we did this, we have water here, right? So this water here will simply come here, protonate this. See, we regenerate the hydroxide that we started with, and we get this right here. Okay, so therefore, we have finished the reaction mechanism. In other words, they ask us to, oh, I'm sorry, yes, here, not that. It's supposed to be here, this one here. Supposed to be this here, okay? Okay, so what we've done here, we're giving you the mechanism going from here to here, okay? And if you notice here, these are all of the reactions that we've done before, essentially Robinson annulation, which is a combination of Michael addition and aldo condensation. In this case, there is no condensation, it's just a straight aldo reaction. Okay. Okay. And that is this one here. After you do the protonation with water. Okay, so now let us, we finish the problem set from your quiz. Now let us, for the time that we have, let's start a discussion on chapter 24. Is there any question on this before we go? Okay. Okay, so what we want to do now, we want to start chapter 24. Of course, chapter 24 is concerned with the chemistry of amines. You guys, of course, know that we have used amines in previous chapters. In other words, you have come in contact with different types of amines. But in this chapter, we are going to actually study the chemistry of this class of compounds. I will discuss the nomenclature, the synthesis, and some of the reactions of amines. On this next slide, simply gives you a list of learning outcome objectives. You should use this as a study guide. In other words, upon completion of this chapter, you should be able to perform all of these activities on this slide. For example, provide names for simple alkenes and design multi-step synthesis using what we call Steinmeier reactions. So all of these things you should be able to do upon completion of this chapter. Now the next question is, what are amines? Amines are organic derivatives of ammonia. Amines are organic derivatives of ammonia. We know that this is ammonia molecule. You notice here, on the nitrogen atom does contain a pair of non-bonding electrons. That pair of non-bonding electrons makes the amines very reactive. Actually, they do react as what we call organic bases. Okay, unlike the alcohols, this non-bonding pair of electrons is readily available to be used as a base as well as used as a nucleophile. Of course, the hybridization of this nitrogen here, this is an sp3 nitrogen. It's an sp3 hybridized nitrogen. That means all of the most of the alkenes that we are going to encounter are the hybridization around the hybridization of the nitrogen atom will also be sp3 hybridized. We do have 4 different types of amines, as you can see on this slide. We have what we call the primary amine. In the primary amine, you notice here, only one of the hydrogen in ammonia has been replaced by a carbon atom. In other words, for the primary amine, the nitrogen is only attached to one carbon atom. So this would be an example of a primary amine. And then we have a secondary amine. In the secondary amine, the nitrogen is attached to 2 carbon atoms. Now, in all of these cases here, you see I have the non-bonding pair of electron on nitrogen. Then in the tertiary amine, we have the nitrogen atom is attached to 3 carbon atoms. Okay, so this is an example of a tertiary amine. We could also have cyclic amine, in which the nitrogen is part of the ring system. Okay, in this particular instance here, what type of amine would this be? Primary, secondary, or tertiary? This here. So secondary amine, very good. So this would be an example of another example of a secondary amine. And finally, whenever the nitrogen atom is attached to 4 carbon atoms, then we say we have a quaternary amine salt. Okay. In this case, the nitrogen is positively charged. That's a formal charge of +1, and of course you are going to have a counter ion which will be negatively charged. So these are the 4 different types of amine that we are going to encounter, that we actually do encounter in nature. Of course, amines are very important organic molecules. Most of your proteins, most of your biological molecules do contain nitrogen, so they will classify as amines. Okay, so now let us now take a look at the nomenclature of amines. Are you writing this? No. Okay, by the way, most of my lectures are also available in the PowerPoint. I'm sure most, all of you already know that in black. All of these are posted in Blackboard. Okay, let's take a look at nomenclature. Of amines. Let's take a look at the primary amine first. When it comes to primary amines, there are 3 different ways in which we are going to name the primary amines. Say, for example, if we use this molecule here as an example, this would be an example of an amine. Now, to name this, like I said, there are 3 different ways in which we can name this. One way is to take a look at the alkyl group that is attached to the nitrogen. Okay, so you give the name of the alkyl group that is attached to the nitrogen. In this case, what would be the name of this alkyl group? Butyl. That would be butyl. Okay, so this becomes butyl. Then you add the word amine, one word. So that becomes butyl amine. So that is one way of naming amine. Another way in which we can name this is to look for the corresponding alkane name for the alkyl group that is attached to the nitrogen. In this case, the corresponding alkane name will be what? What will it be? Butane. And so to name this as an amine, what you do, you remove the E ending and you add the suffix amine. So you add the suffix amine, so this becomes, to also name this as butane amine. Now the third way in which you can name this is to name this as a derivative of, in this particular instance, an alkane, or if you have some other functional group in this molecule here, you name it as a derivative of that class of compound. In this particular instance, therefore, if you are going to do that, that means this group here becomes what we call an amino group. So this will therefore becomes one amino butane if, for example, I have this, now, if you want to name this as a derivative of an aldehyde, what will be the name? This molecule here. Okay, let us number this. Is carbon 1, 2, 3, 4, and 5. So this becomes what? 4 amino hexa. Very good. 4 amino hexa. Now, because at this point you are naming this as an aldehyde. Okay, so those are the 3 different ways in which you name a primary amine. Yes. Oh, I'm sorry, penta. Thank you. Penta now. Thank you. Okay, so those are the 3 different ways in which you name a primary amine. Now, supposing we have a secondary or tertiary amine. In this case, let us use this as an example. Supposing I have this. In this case, you look for the longest carbon chain that is attached to the nitrogen, and you use that as the base name, or sometimes the more complex carbon chain as the base name. So in this case, the base name will be 1, 2, 3, 4. That will be butylamine. So therefore, you then want to indicate that you have a methyl group or an alkyl group attached to nitrogen. So that becomes N-methyl. Then you give the base name. In this case will be butylamine. Or if you want to use the other type of nomenclature, you could simply say N-methyl butanamine. Remove the E ending So you could also do that. Now supposing we have this, now this is a tertiary amine. Okay, in this case, the base name will be the more complex alkyl group. It will be the cyclohexane ring, and then you then indicate that you have methyl and ethyl attached to nitrogen in alphabetical order. So this becomes N-ethyl. Okay, notice you have an hyphen between the nitrogen and the alkyl name, N-methyl, and then you give the base name, cyclohexylamine. Or if you want to use the second type of nomenclature, you say N-ethyl, N-methyl, cyclohexane amine. Okay. Now, when it comes to the aromatic amines, this here, this particular molecule here, yes, of course, we could call this phenylamine. But the name that I would prefer for you to use is aniline, the common name. It is an accepted IUPAC name. Okay? So this molecule is called aniline. Okay, that is what I want you to use. So at this point, I am going to leave the rest of nomenclature for you to study. You have a lot of examples in your textbook, so you should avail yourself of that that resource. So at this point, we want to go to the synthesis of amines. Most of these syntheses we've done before, so this will be like a review to all of you. Okay, to help you out, I will go ahead and number them. Like I say, most of these we've done before. LAH, reduction of nitriles. Okay, that will give you a primary amine, for example. If you have a nitrile and you react with lithium aluminum hydride followed by either dilute acid or water, that will transform a nitride to a primary amine. We've done this in the past, so I'm going to just give you one example here. Notice here, this carbon here becomes, this carbon becomes a methylene carbon. Okay? Okay, so that is why we call this reduction, because we are adding hydrogen across the carbon-nitrogen triple bond. Two, LAH, reduction of amines. Now this is a very good one because you could use a primary amide or a secondary amide. Okay, so this allows you to make both a primary amine and secondary amine and tertiary amine. For example, if you have this, at this point I am assuming that you guys know how to make the amides. If you have this primary amide, lithium aluminum hydride, follow that up with water or dilute acid, the carbonyl is transformed to a CH2. So this carbonyl now is this. Because you know you can make this from the carboxylic acid, Syntheses, and ammonia. Okay, you could also use the secondary or tertiary amide. In this case is LAH followed by addition of water, and so this will give you the opportunity to make a tertiary amine. And this here, carbon here is this right here. Okay, so that is method number 2. Okay, method number 3, LAH reduction of azides. This is new to you guys. This type of molecule here we call an azide. Actually, it does look like this. That is an azide. Okay, to make the azide, you do an SN2 reaction. Take an alkyl, bromide or chloride, or any alkylating agent that has a good leaving group, and you take sodium azide, the sodium azide behave very much like if you have a sodium bromide or sodium iodide. So the azide will simply, this is an SN2 reaction. So the azide will come here, displace the bromide, and you get your alkyl azide. And then when you take the alkyl azide, react with LAH, followed by water or dilute acid, what you obtain is the primary amine. Okay, so reduction of the azide with lithium aluminum hydride will directly give you a primary amine. So that's method number 3. Number 4, Hoffman rearrangement of primary amines. If you take this primary amide here, and you take hydroxide in the form of sodium hydroxide or potassium hydroxide, in water, of course, in the presence of bromine. In other words, you add hydroxide and bromine together, what you get is this here. Plus carbon dioxide. So you are losing carbon dioxide here. So this is this is a reaction or method that allows you to lose a carbon atom in a given molecule. For example, I could take this molecule here, benzamide, okay, benzamide, using this particular reaction is what we refer to as Hoffman rearrangement. This is bromine, now supposing I ask you, okay, this is the Hoffman rearrangement. Supposing I ask you, give me a synthetic scheme. Oh, that was method number 4, right? Okay, we're going to come back to method number 5. Supposing I ask you, was that 4 or 5? That was 4, right? Okay. Suppose, oh, that was 5. That was 5. Oh, is that? I was rolling. Okay, let me finish it. Okay. Supposing I ask you to give me a synthetic scheme going from here to here. Let's do this and then we go. How will you do that? Given reaction that we just given you? Huh? KMNO4, very good. So you want to oxidize this to carboxylic acid, right? Okay, then what do you do with that? Then what do you do? Huh? DCC, oh, okay. So now you want to form an amide with ammonia. And then you do your Hoffman rearrangement. Very good. Then you do your Hoffman. Okay, folks. So when we come back on Tuesday, we are going to finish this, and also as part of the review session on Monday, I will finish the finish the synthesis of amines as part of that session on Monday. So I will see you guys either on Monday or Tuesday. So enjoy your weekend.
Until Monday.
Monday.
Okay.
Okay. Oh yeah, I do have your